Hi, in this video I'm going to give a basic explanation of how position, velocity, and acceleration are connected to each other. Then I will show two examples of questions about this concept. The most important thing to know when dealing with movement in calculus is that velocity is actually equal to derivative of position and acceleration is derivative of velocity. So, as I said, velocity is the derivative of position and acceleration is the derivative of velocity. If you think about it, this makes perfect sense because derivatives show instantaneous slopes. So the derivative of position would show the instantaneous change of x, which is the instantaneous velocity at that point. Another way of looking at it is by stating that the integral of acceleration is velocity and the integral of velocity is position. This, what I just said, is exactly the same as this. It's just reversing it. Instead of making derivatives equal to each other, it's making the integral. To solve an easy question, which will probably help most of you understand what we're talking about. How far to the right did a cart move after 3 seconds if it had a constant acceleration of 2 meters per second squared and started from rest? So from this information alone, we can head on to the acceleration graph and draw a straight line at 2 because the question tells us that it had the constant acceleration of 2 meters per second squared. So this is the acceleration graph, and we can now plug it into this formula, which states that integral of acceleration is equal to velocity. So the integral of 2 dt would be equal to the velocity. So if you want to integrate 2, you get 2t. So right here, 2t would be the graph of velocity. So we can now draw the graph of velocity, and since it says that the cart started from rest, we can conclude that the beginning point would be right here at t equals 0 and velocity equals 0. So the graph would look like this, and some of its points would be t equals 1 is 2, t equals 2 is 4, t equals 6 as t equals 3 would be 6. So this is a graph and it's linear. So now we can integrate it once more in order to find the graph for the distance. So the integral of 2t dt would be t squared. And right here, t squared is the graph of distance. So I'm going to color it in a different color. So right here, this is the answer that we're looking for. And so we can now simply plug in 3 seconds to this, and if you plug in 3, you get 9, because 3 squared is 9. So now we can go back to the graph of distance and plug in 9 right here. And then if you plug in 2 to here, you get 4. If you plug 1, you get 1. And if you draw a line between all these, you get an exponential graph, which makes sense because it's the graph of t squared, and that's the graph of how far the cart was moving. So as you can see, if the acceleration is constant, the velocity will increase in a linear way, and the distance will be exponential. The next thing we're going to do is discuss another way of finding the velocity and position at any given point. So the other way is using definite integrals or also area under curve. It's basically the same thing. So the question again is the same question. How far to the right did a cart move after 3 seconds if it had a constant acceleration of 2 meters per second squared and started from rest. So you know that the graph of acceleration is straight again, right? So what you can do in order to find the area on the curve, of course in this case you could just do 2 times 3 because it's just a perfect square. But if it were a harder question, you would take the definite integral from t equals 0 till t equals 3 because the cart was moving for 3 seconds. Okay, you do of 2 dt. This is equal to 2t from 0 to 3. Okay, and then you do you plug in 3, so it becomes 6 minus 0, which is 6. So that's your answer. So at t equals 3, velocity would be 6. Right here, which is exactly the same as what we got before when we did the integrals and then we plugged it in. So velocity 6, and then you can do another. So you know velocity has to be a straight line. So you can do another definite integral to find all this area under the curve. So it's the definite integral of 0 to 3. You know that the graph of velocity is 2t. So dt. Sorry, it kind of got smushed together. So this is the same thing as t squared of 0 till 3. So you plug it in again and you get 9 minus 0, which is 9. And that's your final answer, 9 meters. Because at t equals 3, the area on the curve, under the curve of the velocity is 9, which means the point here would be 9 too. So what we've learned from here is that the area under the curve in acceleration gives you the point on the velocity graph, and the area under the curve in velocity gives you the point in the distance graph.